Thank you. Thank Andrei Mikhailovich Yagorsky for inviting me to make a talk. I'm going to tell about 0-1k loss for Erdős-Rényi random graph. So it's about asymptotical behavior of probabilities of first order properties of this graph. Let me start from the definitions. So first order properties are expressed by first order formula which are built of the following symbols, relational symbols. So the first one is a symbol of adjacency, and the second one is the symbol of coincidence, then logical connectivities, variables, and quantifiers. We need variables to express the vertices of the graph. For example, this is the first order property of a graph to be complete. And this one is property of a graph to contain a triangle. It's also the first order property. And for example, property of a graph to have hermetic number k is not first order property. It cannot be expressed in terms of this language. Okay, and now Erdős-Rényi graph G of n P, where each h appears with probability p, and n is number of vertices. So let's start from some simple properties. Let G be an arbitrary graph and consider a property of containing this graph. We denote it by LG. And we consider maximal density of the graph. It is the maximal value of this fraction, number of edges of H, over number of vertices of H. And denote by P0 this function. So it was proved by Balabash that if P is asymptotically greater than P0, then probability of this property tends to 1. And if P is asymptotically smaller than P0, then it tends to 0. And if P is P0, then there is a limit probability which is not equal to 0 or to 1. So we can conclude immediately that if we consider this set of properties, so for each property from this set, we have a graph G such that this is the property of having graph G as a subgraph, or it is a property that there is no such a subgraph in our graph. So if probability P equals n to the power minus alpha, and if alpha is irrational, then of course the probability of L tends to 0 or to 1, because each threshold is this function, and it cannot be equal to n to the irrational power. So so we have this probability only for probabilities when alpha is rational. And it was proved by Spencer and Shelah that we can consider a wider class of properties, all first order properties. So let L be the set of all first order properties, and we say that the random graph obeys 0-1 law if for any first order property, its probability tends to 0 or to 1. And so it was proved by Spencer and Shelah in 1988 that if alpha is So if alpha is irrational and alpha is positive, then 0-1 law holds. And if alpha is from this interval and it's rational, then 0-1 law doesn't hold. Okay, and so the question is, can we consider some subclass of all first-order properties such that alpha is rational from this interval, but 0-1 law holds for this smaller subclass? And the answer is the following. We can bound quantifier depths of the formula, and then we will find some rational alpha from 0-1 interval such that 0-1 law holds. Let me remind the definition of quantifier depths. So if there are no quantifiers, then quantifier depth equals 0. If quantifier depth of a formula equals k, then quantifier depth of negation of this formula equals k as well. So if you have two formula with quantifier depths equal k1 and k2, then quantifier depths of all this formula equals maximum of k1 and k2. And finally, if we have some formula and we have a variable x, then quantifier depths of these two formula equal k plus 1. So we say that random graph G of NP obeys 0-1 law if for any first-order property which can be defined by formula with quantifier depth bounded by k, its probability tends to 0 or to 1. So I said that the property can be defined by a formula because there can be different formula which define the same property, and in this case we take the minimal quantifier depth. So for example, this you can see two formula which express the same property, and then we consider quantifier depths too. So let me start from simple examples. It can be easily proved that when alpha is positive and less than 1 over k minus 1, then 0-1 k law holds. And the proof of this fact is similar to the proof of the theorem of Glebsky and others, which was proved in 1969. So if p is such a function, for example, a constant or 1 over log n, then 0-1 law holds. So the proof is simple, and the proof of this fact is totally similar. But what happens when alpha is greater or equal than 1 over k minus 1? So, for example, we can consider the most dense graph on k vertices. It's a complete graph, and consider its threshold probability. So from theorem of Bell-Bolbach, we know that it equals to n to the power minus 2 over k minus 1. And then we get this point. So if alpha equals 2 over k minus 1, then 0-1 k law doesn't hold. In such situations, I will say that this point is k critical. So if there is no 0-1 k law, then the point is k critical. So 2 over k minus 1 is k critical points. It's a k critical point. But what is about this interval? Are there other critical points? And the answer is yes, there are. And so I proved that if alpha is less than 1 over k minus 2, then 0.1 kilo holds. But, okay, it will be on the other slide, but if alpha equals 1 over k minus 2, then it doesn't hold. So 1 over k minus 2 is the first positive k critical point. And then let's consider another interval which is close to 1. So maybe it's difficult to read. Maybe it's simpler. So here you can see intervals where 0.1 kilo holds. So it's near the point 1, and then we proceed with other intervals. So if here we consider the points that are greater than 1 minus 1 over 2 to the k minus 1. And you can see here that beta is positive, so alpha is greater than this number. And so if the result is the following: if alpha equals this, and beta is not from this set, so if the numerator of beta is rather large, then 0.1 kilo holds. And okay. And if, so here you can see that if alpha is equals 1 over k minus 2, then it's a critical point, k critical point. And here you can see other k critical points from this set. So if beta is in this set, I don't know always if 0.1 kilo holds or not. But I know that if we have these points, then 0.1 kilo doesn't hold, so this is a set of k critical points. And I have an illustration which can make this simpler. So here I list k critical points when alpha goes from 0 to 1. So the first one is 1 over k minus 2. Then we have a large gap, and we don't know anything about it. And then the first k critical point that we know is 1 minus 1 over 2 to the k minus 1. And then some points and some intervals, we know something about that, but not everything. Here it should be 1 minus 1 over 1 minus this fraction. There is a little mistake. Okay, and all other points are k critical, and we know. So the first one here is this, and we know all the others. And the last one is 1, not 0, of course. So 1 minus 1 over 2 to the k minus 2 to the k minus 2, and so on. And the last 3 k critical points, you can see it. So let's consider small k. So what happens when k equals 3? So when k equals 3, there are no k critical points in 0-1 interval, and of course the point 1 is 3 critical, but there are no others. And then k equals 4. So this interval from 0 to 1/2 is, there are no k critical points, and the point 1/2 is 4 critical. And then we have this interval. There are also no 4 critical points. And we know something about this interval. And we know also that all these fractions are 4 critical. And one more result, we know that there is no 4 critical points in this interval. Okay, so it's rather simple to prove that all these points are 4 critical, and it's very simple to consider these 4 points, and I will do it. On the next slide, I will prove that they are really 4 critical. So once again, here you can see all that we know about all k. K equals 3, k equals 4, and k is greater than 4. So when the interval is blue, then there are no critical points, and the red points is for critical. So let's consider the case alpha equals 2/3. Then we just should consider the property of containing complete graph on 4 vertices, because its density and its maximal density equals 3 seconds, and so its threshold probability equals n to the power minus 2/3, and of course its probability doesn't tend to 0 or to 1. Okay, it's simple, and so if alpha equals 3/4, it's not so simple, because can I use board? So if you consider just a graph on 4 vertices, then we can only have 2 situations when it's complete, and then alpha equals 2/3. And when we remove one edge from this graph, and then alpha equals 4/5, because it have 4 vertices and 5 edges, and so we can't prove anything for alpha equals 3/4 in this situation. But here I consider this formula. So when we consider only graphs which doesn't have a small subgraph with density greater than 3/4, so if we consider only a class of graphs with no subgraphs, with no small subgraphs with density greater than 3/4, then the following 2 properties are equal. The property that is expressed by this formula, and the property of containing this subgraph. So, and this subgraph have maximal density for 1/3, and therefore its probability doesn't tend to 0 or to 1. So we don't have 0-1 law, because because the depth of this formula equals 4. So this case, 4/5, I illustrated here. So we just consider the property of containing complete graph on 4 vertices without one edge, and we have threshold probability equals n to the minus 4/5, and so it doesn't. The probability doesn't tend to 0 or to 1. And if alpha equals 5/6, then we can consider this formula, and again, if graph doesn't have small dense subgraphs, then it should contain this graph, but its probability doesn't tend to 0 to 1. Well, all 0-1 laws are proved by using the theorem of Ehrenfeld, which was proved in 1960. And first, let me tell you about Ehrenfeld game. So let me have 2 graphs, G and H, and K be a number of rounds in this graph, and we have 2 players, spoiler and duplicator. So in each round, each player makes a move. So each player chooses a vertex from a graph, and in each round, spoiler chooses any graph that he wants, and duplicator chooses another one. So if in the first round, spoiler chooses this vertex, then duplicator in this round should choose any vertex from this graph, for example, this. And then in the second round, spoiler can choose a vertex from this graph, and then duplicator should choose a vertex from this graph. And let k equals 4, so we have 4 rounds, and after the 4 rounds, in this graph we have 4 chosen vertices, and in this graph too we have 4 chosen vertices. And duplicator wins if and only if these subgraphs are isomorphic. So in these situations, duplicator wins. Okay, and it was proved in 1960. So it was proved for any finite structures, but I will tell only about the graphs. Let G and H be 2 graphs. Then for any first order property L expressed by formula with quantifier depth bounded by a number k, this property holds if and only if duplicator has a winning strategy in the game on graphs G and H with k rounds. So for the illustration, let us consider this formula. It expresses the property of a graph to have a triangle, and we have one graph and the second one contains a triangle and the first one doesn't. So it follows from the theorem that spoiler wins a game in 3 rounds, and he just chooses these 3 vertices, but duplicator cannot find in this graph such 3 vertices that it will be a triangle, so spoiler wins. Okay, and it's not very difficult to see that we have the following corollary from the theorem, so I'll start from this one. Random graph G of P obeys 0, 1 k law if and only if with probability tending to 1, duplicator has a winning strategy in the game on k rounds. And of course, simple 0, 1, not 0, 1 k law, but 0, 1 law holds if and only if for any natural k, duplicator has a winning strategy in the elephant game with probability tending to 1 in the game on k rounds. So if you want to prove 0, 1 k law or 0, 1 law, we just prove this corollary. Not this corollary, but we prove that duplicator has a winning strategy in the game on k rounds. Okay, and now let me list the most interesting open questions that we have. So we have this large interval from 1 over k minus 2 to 1 minus 1 over 2 to the k minus 1. Well, I recently proved that this point is k critical, so we shouldn't include it into this interval. And so I think it's more interesting problem. Spencer and Shelah proved that there is such a property that there is an infinite number of rational numbers in 0, 1 interval such that all these numbers are critical. So if p equals n to the power minus alpha, when alpha is from this set, then probability of this property doesn't tend to 0 or to 1. But let me remind you that if we fix any positive epsilon and consider this interval, then from my result it follows that in this interval the number of k critical points is finite. So, but what happens when epsilon equals 0? So does this property hold for this interval? And what is the maximal k such that there is finite number of k critical points? Well, we know that if k equals 3, then there are no k critical points in 0, 1 interval. But we don't know what happens when k equals 4. So is this number critical or not? And also we have small k equals 4 and k equals 5, and there are a lot of gaps, and we should receive new results. Okay, thank you very much.
We have 4 minutes for questions.
So let me concentrate on alpha small. Concentrate on alpha near 0, and if k is large, so you have 1 over k minus 2
Yes.
is the first value, but do you know or do you have a conjecture what is the second value?
No, I don't have conjecture. So I didn't think about it too much, but it's rather difficult.
More questions?
Thank you. So what if you consider the hierarchy? So in logic, one usually counts the number of quantifier changes rather than, you know, the number of quantifiers and forth. So I suppose you will obtain somewhat different results for this modified notion of k critical point and so on.
Yeah, thank you. Well, I can say that if we have only one, at most one change, then the same results hold. But no, not the same. If the number of changes is can be greater than 2, then the same results hold. But there should be some different situations when the number of changes is small.
If we have no more questions, let us thank the speaker once again.
Thank you.